recording? Okay. All right, so just to let you know, okay, for this course, is it okay? I would like to ask for your cooperation, right? So can you please don't touch any of the button. For example, you establish yourself the meet button, right? Because I already scheduled for a meeting, right? And some of you just simply click the meet button, okay, which is sometimes being recorded as general meeting, okay? Because I already scheduled it and I named my lecture as lecture 2, right? So if you just simply click the meet button, all right? I know that some of you prefer to come early to the class, okay, since it's online. So you just prefer to come early, so you just click the general button. So I would like to ask for your cooperation. Don't do anything, okay? Let the host do it, right? And also the recording session, okay? If I don't record the session, you can just give me a reminder for that, all right? Because in my previous class, in my other lecture class, right, some of the students did that as well, but they have problem with the recording session, right? Because when the host is not doing the recording session, sometimes the recording will have, will stop in the middle, right? Because I remember in my statistics class, okay, because I have like a huge class, it's around 200 students, and some of them are very like tangan gatal, I can say. It's very like concerned about not recording the lecture. So I was actually giving them an announcement, right? But at the beginning of the course, just ask them like, can you please sign into your attendance? And they are like eagerly want to record this session, right? So what happened, okay, after 10 minutes, it's just dropped. Okay, I know that one of the reason the internet stopped the session being stopped recording is because of the internet problem. But one of the issue is because that it is not done by the host, right? So please, please give your cooperation for a recording session. Please allow the host to do that. If let's say the host forgot to click the recording button, you can just simply remind them, okay? And also for the meeting session, right? Don't just simply click the meet button, wait for the host to call you, right? Because or else like it give you no point, right? Like why I already schedule for a meeting, and every meeting has the name like lecture 2, and then when you want to simply click the meet button, it will give you like a general meeting, right? So I hope that please allow me to do everything, okay? Or else like I will assign one of the class rep to do it for me, right? Okay, so enough talking. Let us continue with the um, with the lecture. Okay, so continue with the hazard function. It's too small. Is it too small? Okay, so I just enlarge it. Okay, what is the hazard function? The hazard function is okay, hazard function is actually a probability that individual dies at time t, conditional on he or she survived to that time. Okay, so that is the survival function. Okay, you are looking for a probability for a die patient, okay, at time t, right? Okay, conditional, he or she survived to that period of time, okay? So the hazard function is the limiting, okay, function, right? So you limit delta t greater than 0, which is, it is equals to probability t between t and t plus delta t, which is conditional on t greater than or equals to t, right? So divided by delta t, right? So this is actually called the instantaneous death rate. Okay, I also don't know how to explain this, right? Okay, because I also like how to calculate the instantaneous death rate. Meanings what? Like you know, like you are known to be death and at time t, and you are looking for the probability of death rate. Okay, so that is the meaning of that hazard function. Okay, so this hazard function, or HT, equals to the limit of delta t approaching to 0, where t is between t and t plus delta t. Okay, so this one, okay, have you seen this function before? This is similar to the Bayes rule, right? So given that probability of A given B, okay, so in this case, your probability A, okay, P of A, okay, equals to the probability of T less than T, less than or equals to T, and it is T plus some value of delta T. Okay, so this is your A. And then your PB is equals to probability of T greater than or equals to T. Okay, so right, so probability A given B is equals to P A intercept B divided by PB, right? Okay, so apologize about my handwriting and also with my pen. Blame my pen, okay? All right. So this is actually the Bayes rule. So you apply the Bayes rule into these instantaneous death rates, right? You are looking for death rate, okay? So this is actually probability A intercept with B, okay? So this is your B, this is your A, divided by PB. PB is probability T greater than or equals to T, okay? So this is actually equals to Ft plus delta T, right? So what is F? F is actually probability T less than or less than T, which is Ft plus delta T minus your Ft, right? Divided by delta T. Okay? So this is times with 1 over probability T greater than or equals to T. Okay? So this is actually equals to Ft over St. Okay? Right? Okay, so any questions so far? Right. So none of you asked me a question like, how can you, from here, you get it here? Okay, so again, the Ft is actually probability T less than or equals to, not less than or equal, is T less than T. Am I right? So, and you know that probability T greater than or equals to T is actually, is the probability, is a subset of probability T between T and T plus delta T. Okay? So that is why it is equals to Ft plus delta T minus Ft, right? So this is actually, I just put it here. Okay, so this is equals to limit, right? Delta T approaching to 0. Okay, this is so messy, right? Why don't I just open in Microsoft PowerPoint so that I can just simply copy and paste that thing. If you don't mind, okay, I just open because I just want to do a lot of calculation, handwritten one, okay? It's a PowerPoint. All right. Hey. Okay. So yeah, can I just and paste? Okay. Hmm. And copy, right? So just have a copy. Okay. So alternate copy. Very old school. Oh no. This I should crop that, right? Any idea on how to just crop for that? Uh, I wish I can do crop. Clip art, not the clip art. Not the clip art, right? I don't know how to do the clipping thing. It's okay. So just show to you that, again, I just want to describe about the HT. Okay, again, just write it here. FT, this is quite smooth, right? So this is equals to probability of t less than t, okay, which is integral of 0 to t of your fu du, right? And your st equals to probability of t greater than or equals to t, which is 1 minus f, right? So it's a survival function. Survival function is actually a patient who is survived after time t, right? So that is survival function. Now, what is the HT? So HT is actually limit of your delta t approaching to 0 of your probability of t between t and t plus delta t. All right. Given that t is greater than or equals to t over delta. This is the okay. So this is an instantaneous um, death rate. Okay. So this one we are using the Bayes rule. Okay. What is the Bayes rule? Probability A given B equals to P A intercept with B, okay, divided by P. Okay, and then are you done? Are you done for that part? It's missing here. Hilang. Okay, so this is actually PA intercept P over PB. Okay, so yeah, it's missing here, right? Bayes rule. Right, so right again, continue, okay? Okay, so HT is actually equals to limit of your delta t approaching to 0. For this, sorry about my curly bracket, it's very ugly, okay? So it's a probability of t less than or equals to t and t plus delta t, right? And then intercept with t greater than or equals to t, right? So divided by delta t times with your probability t greater than t. Remember, it's PA intercept B divided by PB, right? So again, for this one, right, when you intercept this thing, you know that t greater than t is actually a subset of your t in t, okay? So this is actually equals to limit delta t approaching to 0 of t, t less than or equals to t and t plus delta t, okay? Right? Over delta t, t greater than or equals to t. Okay? Because t greater than t is actually a subset of t less than t, t plus delta t. Okay? Right. So this one, okay, if we want to relate it with ft, and you know that your ft is this. ft is probability t less than t, right? So in this case, okay, this is equals to limit delta t 0. This is f t plus delta t, right? This one, this part, okay? And then minus of your ft, this one, okay? Divided by delta t. Here is your 1 over probability t greater than t is actually your st. Yeah, here this one, okay? This one, okay? So this is 1 over st. It looks like delta. Okay, just have to make sure that my s does not, it's not my delta t, right? So just check s. Okay, so this one ft plus delta t minus ft is actually your ft. Okay, so this is equals to ft over your st. Okay, so this is how we get that thing. Okay. Okay, so that is how we got this from for equation 1.3. Okay. Now, based on equation 1.1, 1.2, and 1.3, you can calculate the HT. HT equals to negative d over dt ln st. Okay. Right. So why am I writing in this form? Okay, because at the beginning, I just explained that HT equals to FT over ST, which I shown in my PowerPoint slide. Okay, so this HT, okay, also can be written as the cumulative hazard function. Okay, so how are we going to relate between ST and cumulative hazard function? So ST equals to the exponential of negative HT. Okay, right? So where ht equals to integration of 0 to t hu du, which is the cumulative hazard. And also we can write down ht is equals to negative log st. Okay, so this is how we relate equation 1.1, 1.2, and 1.3 with HT and ST. Okay, so any questions so far? So that we can move on to the example. We have two examples here. Okay, one is the constant hazard. Okay, and then another one is the verbal distribution. Okay, we can also calculate the ST and HT for verbal and constant hazard. Any questions so far? Okay, so no question from the students, right? Okay, so is that okay if we take like a 5 minute break to refresh yourself and then we come back with these two examples and then yeah, and then to discuss these two examples, and then later we are going to move on uh, to another topic called the some non-parametric procedures. Okay, so you agree for 5 minutes break to refresh? Okay, so are you back? So now we are referring to these two examples, okay? One is about the constant variance and another one is about the verbal distribution, okay? And then we are going to derive the functions, which is the survivor function, okay? And then it is given that if you have an instantaneous death rate, which is constant, what is, because we know that there is a relationship between hazard function and also survival function. Okay, so from that, we can also derive our survival function ST, and from ST, we can get the cumulative hazard functions and also the probability density function, okay, which is FT, okay. Now, I just share with you the PowerPoint slides, the blank PowerPoint slides to show these two examples, right, on how to calculate them, right? So we are now in example 1. So in this example 1, okay, we are looking for a constant hazard, right? So a constant hazard, right? So a constant hazard, HT. My pen. Where's my pen? HT is equals to lambda, right? So we have this hazard function and we know the relationship between HT and ST, where HT is equals to HT equals to, we know that earlier we have shown that HT equals to FT over ST, or HT equals to negative D over DT ln of your ST. Okay, so which is equals to ST equals to, okay, earlier, okay, we have shown that HT is equals to negative D over dt of your ln ST, right? Okay. Now, we want in ST term, right? So, right? So, ST is equals to, okay, so it's no ln ST, okay, because here ln ST equals to integrate from 0 to t, sorry, negative 0 to t hu du, am I right? Okay, so ST, therefore your ST is equals to the exponential of integration 0 to t of hu du, right? Okay, since that we have ht equals to lambda, then we have negative here, right? So it's supposed to be negative integrate. Okay, I missed negative part. Okay, so here, this is the negative one, right? So since that ht equals to lambda, then your st when ht equals to lambda, then st is equals to exponential of negative integrate 0 to t, okay, lambda du. Am I right? Okay, so this is equals to e of negative lambda t. Am I right? Okay, right, that is ht, right? We can also calculate the cumulative function, Okay, so we can also calculate the FT. Okay, we have also derived that HT is equals to FT over ST. Okay, and you know that your ST is E of negative lambda T, right? And now your FT is equals to HT times ST. Okay, what is HT? HT equals to lambda. What is your ST? You have calculated your ST, which is E of negative lambda T. So that is how we get FT. Are you okay with that? The next one is HT. Okay, so HT is equals to negative log ST. Yeah, because earlier we have shown that HT equals to negative D over DT ln ST, where ST equals to E of negative HT, right? So since that the cumulative function is equals to integration of 0 to T HU du, right? So then your HT equals to negative log ST. So in this case, this is equals to negative log. What is your ST? ST is E of negative lambda T, right? So this is equals to log and exponential is become the value itself. That is the negative of negative lambda T, which is equals to lambda T. You okay with that? Right? So what can we say here? So we can say that T is actually an exponential distribution with mean negative lambda. Okay, sorry, mean, lambda to the power of negative 1 or 1 over lambda. Okay. Okay, so the next one is when you have a verbal distribution has a function. Are you okay so far? Okay. Right, so the second example. Okay, so example 2, given that your HT coming from verbal distribution, which is equals to AB T to the power of B minus 1. Okay, so in earlier part, I have shown to you that ST equals to the E of your negative integration lambda 0 to T HU du, right? So if you want to calculate the ST, okay, so we know it's a exponential of negative, okay, negative 0 to T HU du. Okay, now it is equals to your HU is equals to ABU B minus 1. Okay. Okay, so this is equals to exponential of, okay, negative, right? So A, B, this is U to the power of B over B. We cancel B, it becomes A, U, B from 0 to T, right? So this is equals to exponential of negative A T, okay, it's no, yeah, yeah. T, B minus 0 is 0, okay, so negative 80, okay. So it is similar answer, of course, you can get the same one, but this is how you derive it, okay, from the lecture notes, right? And then you can also calculate the FT, okay, and also your HT, okay. So the FT is equals to HT times your ST. So your HT is equals to ABT T B minus 1 times with your exponential of negative 80, okay, which is equals to, okay, right? So it's A, B, T, B minus 1, E of negative 80, right? I cannot simplify them, right? So I just change it instead of exponential, just E to the power of negative 80B. Okay, I'm missing something, right? So this is actually AT to the power of B, right? So you have ATB, okay? The next one is your, can we calculate the cumulative function? Of course we can, right? But even we didn't show it here, but we can simply calculate them, okay? Right, so we just show that HT equals to negative log ST. What is our ST? ST is e to the power of negative AT to the power of B. So negative log E, okay, negative AT to the power of B. Okay, so it is equals to negative, okay, log E become the value of here. So negative AT to the power of B, which is equals to AT to the power of B. Are you okay? Okay, so this is how we play around with the function of the survival function, the hazard function, and also the cumulative distribution function. Okay, so yeah, so now it's 7:03. Um, if you don't have any question, we shall proceed with some non-parametric procedure. Uh, do I have the lecture notes? Just a moment. The lecture notes. Oh, this is the log rank test. The lecture notes. Oh, okay. So the one that I've uploaded here is actually the lecture note that I've uploaded here is actually the lecture notes, which is about the log rank and also the Wilcoxon test. Okay, but I didn't upload um, the Kaplan-Meier and also um, the Kaplan-Meier and also the live table plot, right? So apologize about that. Okay, I have missing um, one lecture notes. Where is that? Oh, oh. Okay, so I just found the lecture notes here, but I didn't upload it in Spectrum yet. So yeah, just want to have a quick recap. Okay, so okay, right. So just share with you the lecture notes, right? Regarding lecture 2. Okay, so and it's very, very small. Okay. Okay. So this is about non-parametric procedures, right? So the non-parametric procedures for survival analysis is actually you are playing around with the survival function, with the hazard function, and also with the cumulative um, hazard functions, right? So the ST, the HT, and also the capital HT, right? So to do the survival function, okay, since that we only get the sample size, so what we can do is we are doing some estimation of your survival function, right? So in this case, if you look in this lecture note, okay, which I didn't upload yet in your Spectrum. However, I just want to show because this is the application part, okay? So this survival function, ST, can be estimated by the empirical survival function, okay? So we represent that by S tilde. S tilde is the estimated one, which is the number of survivor or number of individual who is survived at time greater than T divided by number of individuals in your data set. Okay, so you can see here, okay, because I have mentioned to you earlier that ST is equals to 1 minus FT. Okay, okay. So if you recall back that your ST is equals to probability of T greater than T, okay, which is equals to 1 minus ft, which I have mentioned earlier in this chapter. Okay, so to do this estimation of your ST, it is actually a number of individual who is survived after time t divided by number of individuals in your data sets. Okay, so this ST is equals to 1 minus FT, which is similar to this one, but since it is in the empirical survival function, so we just represent FT with F tilde, right? So F tilde is the empirical distribution function given by F tilde T, number of individual who's still alive at time T, divided by number of individuals in your data sets. Okay, because number of individual who's still alive, okay, at time T is actually probability T less than T, right? So just to give a recap, Ft equals to probability T less than T is equals to integration 0 to T Fu du, right? Okay, so this is how we are applying to estimate the survival function and also the distribution function. Right, so this S tilde T and F tilde T can be applied if none of the data is censored, as the method failed to make use of the information on censored observation. Meaning that if you want to apply these rules in survival data, it is very, very difficult because one of the criteria for survival data analysis is the censoring data. Okay. So before we move on to the Kaplan-Meier estimation survival function, let us move on to the life table. Okay, I believe that some of you who are from actual background, you have learned about life table, right? So on how to compute the life table, these are the following steps, right? So here we have DJ is the number of individual who number of death. CJ is number of censored and NJ is number of alive, right? So one of the assumption that need to be made is the censored survival time is assumed to occur uniformly throughout the jth interval, meaning that you must have the same censored observation at each jth interval, right? So the average number of patients at risk of death during jth interval is n prime j equals to nj minus cj over 2 because cj is uniform, okay, as mentioned earlier. And then the probability of death is equals to dj divided by n prime j, okay. So the number of patient who are, the number of death divided number of patient at risk. Therefore, your survival probability is n prime j minus dj over n prime j. All right. All right. So now, okay, so you have looked into the first procedure, okay, to use the life table, which is you divide your study into several intervals, right? Which is from time point tj until to time point tj plus 1, okay. So, sorry, you divide them into several intervals called m intervals, and for each intervals, okay, or the j interval, right, it's actually time from tj to tj plus 1, okay. And then the procedure number 2, you need to identify what is your dj, your cj, and your nj. What is dj? Number of death. What is cj? Number of censoring in your j interval. What is NJ? Number of patient alive, right? So, and also you need to make an assumption that your CJ need to be uniformly distributed throughout your J's interval. And then finally, you can calculate your probability of surviving in J's interval, where it is equals to S star. S star equals to the product from j equals to 1 until kth interval of n prime j, which is the number of death, right? Minus, sorry, not number of death, number of risk minus number of death divided by total number of risk, okay? So T is between K and K plus 1. This is for survival at one interval, okay? So K from 1 until M. Okay, so these four procedure to produce the life table. Okay. Right. So please take note here that using this life table, it is actually very, very sensitive to the selection of interval. Okay. So but it is good for interval censored survival data, right? Okay, so that is about the life table, right? So this is actually to sum up. Okay, this part is actually to use the survivor function and also the hazard function. Okay, so at the first part of this lecture, I am actually ex, uh, um, exposed to you the what is the survivor function and also the hazard function and how to derive them, right? And in this part is how you apply the survivor function in your sample data, right? So we have two methods for survivor function, which is using the life table, and the next one is using the Kaplan-Meier um, estimates of your ST. Okay, so Kaplan-Meier or product limit estimator. Okay, right. So we move on to the next example, which is not next example, the next part, which called the Kaplan-Meier estimate. Okay. So this example, we are going to use the survival of multiple myeloma patients, right? So this example 2.2 can be obtained in your textbook. Okay. If you go to this chapter 2.2, yeah. Right, so before that, okay, before we move on to the Kaplan-Meier estimates, okay, since I already explained to you about the procedure of using the life table, is that okay if I give you an example on how to use the life table and how to calculate the life table? Sorry. Okay, so I just want to share with you this example. Okay, we are using the example 2.2, which is the survival of multiple myeloma patient. So this survival of multiple myeloma can be obtained in chapter 1, which is in table 1.3. So I just refer to table 1.3. Sorry, example 1.1. Okay. Okay, this is not the one that we are looking for. Okay. Yeah, we are looking for example myeloma patient. Okay, so let me just read about this example. What is breast cancer? It's a myeloma, right? Yeah. So if you look at this explanation, the description of the data, multiple myeloma is actually a malignant disease characterized by plasma cell. Okay, abnormal plasma cell. Too big. Okay, so right. So um, right. So abnormal plasma cell, which is a type of white blood cell in a bone marrow. Right. So this myeloma patient is actually, it's not a leukemia, right? I don't think this is a leukemia. This is actually abnormality in your plasma cell. Okay, because we have red blood cell, white blood cell, and also plasma cell, right? So the proliferation of the abnormal plasma cells within the bone causes pain and the destruction of bone tissue. So patients with multiple myeloma also experience anemia, hemorrhage, recurrent infection, and weakness. So unless treated, the condition is invariably fatal. So this aim of the aim of a study carried out at the Medical Center of University of West Virginia, USA, to examine the association between the value of certain explanatory variables or covariates and the survival times of patients. So in the study, the primary response variable was the time in month from the diagnosis until death from multiple myeloma. So in table 1.3, okay, it's obtained from Kral, Uthoff, and Halley in 1975 paper, okay, where we have 48 patients, okay, where all are between 50 to 80 years old, okay. Some of these patients is still survived by the time the study was completed. So these individual contribute to right-censored survival times, okay. So this okay, so 48 patient, some of the patient survive until at the end of the study. Okay, so these are the example of the right censored. Okay. All right, so the coding of the survival status of an individual in the table such that 0 denotes a censored observation and 1 denotes death, okay, so event, right, from multiple myeloma. So at the time diagnosis, the value, so where is the table 1.3? Okay, so this is the table. So we have status 1 and 0. 0 represent they survive, 1 they died. Okay, so we have this patient number. We have 48 patients altogether. Yep, so we have 48 patients. Reduce the size. Okay, so we have other covariates such as the age, sex, BUN, CA, P cells, and protein. So we have 7 covariates, okay, with where we also have the survival times of the patient, okay. Right, so here Table 1.4 give the data recorded for 38 patients where the survival times are given in months. The survival times of patients who died from other causes and who were lost during the follow-up process are regarded as censored. Okay, you see that if you look at the censoring, it is um, if you don't apply the survival function, you just record this die from other causes or lost to follow up as a missing data, right? But for the survival data, we consider them as a censoring, censored patients, right? Because this patient does not experience the events, right? So therefore, we call them the censored data, right? So a variable associated with the status of an individual at the end of the study takes the value unity if the patient has died from, no, this is the different one. Okay, sorry about that. Okay. Investigate the effects. Okay, so this is the table 1.4 with 7 covariates. Sorry about that. Okay, table 1.4 is actually different. This is a table 1.4 is about a cancer patient. Okay, so this table 1.3 is about the patient who on a multiple myeloma. The reason that I show you this table is because that I want to show you on how to calculate the life table, right? Okay. Um, okay, this one. This is the simple one. Um, right, so this is the example of table. Right, so this is um, the data on how to calculate the, based on the data set that we have, right? How are we going to calculate the life table, okay? Say that, okay, you have 6 intervals, right? Where your interval should have an equal length. Okay, it can be unequal as well, but yeah, because if you see the notes there, okay, so um, the life table is actually quite sensitive to the selection of intervals, right? So remember here that you need to select your interval carefully for your life table, okay? So in this case, I just divide them into 6 intervals, right? And since that the table have time from 0 until 60, okay? So therefore, this table is actually summarized the table 1.3, okay? So we have an equal length time. Okay, so time period we have 0, 12, 24, 36, 48, and 60. Okay, so at this time, the first time period, we have 16 deaths, right? And then for the second interval, we have 10 deaths, 24, 1, 36, 3, 48, 2, and 64. Okay, and then the CJ, right? The CJ number of censoring for the first time period is equals to 4. Okay, because as I said earlier, we should have an equal censoring. Okay, if you look at the second procedure for this life table, okay, um, the censored survival time is assumed to occur uniformly through the jth interval. Okay, therefore, supposedly we are having the equal length of your CJ. But it's also possible to have unequal CJ. So here, your first period, CJ is equals to 4. The second one is 4. The third one, 0. The fourth one, 1 censored observation. The fifth one is 2. And the last one is 1. Okay. From that, you can calculate your NJ. NJ is the number of person who are at risk. Okay, so we start with 48. Okay, so here we start at 48, and then 48 minus 16 minus 4, okay, which is equals to 48 minus 20, which is equals to 28. Okay, the third one is how can we get the value of 40? Okay, so okay, the third one is 28. How can we get 14? Is because 28 minus 14 is equals to 14, right? And the next interval is because that 14 minus 1 become 13, okay? And then 13 minus 4 equals to 9. 9 minus 4 equals to 5, okay? So we just stop until the sixth interval. Okay, so the final one is 5. Okay, so you can see it is tally up. Okay, 5 equals to 4 death and 1 censored observation. So it's tally. Right, so to calculate the patient who died, okay, which is, no, not died. The patient who at risk is actually equals to, why is it 46? Okay, because a patient who at risk. Okay, so here it does not include a patient at that time point. So that is why it is equals to 46, not 48. Okay, right? Because here is 0, we have 4 censoring and then 16 death, but n prime j is equals to a formula. Remember, the formula is n prime j equals to nj minus cj over 2, right? So how do you calculate 46? 46 is equals to nj 48. Okay, we calculate this n prime 1, okay? Which is equals to 48 minus, okay, Cj over 2, okay, which is 4 divided by 2, which is equals to 46. Okay, got it? So you can calculate the second number of at risk for the second interval and so on, right? And then, right, because our target is to calculate the empirical survival function, right? So for that, you need to calculate the n prime j minus dj over n prime j, which is equals to the s star, is it s star c at each interval? No. Yeah. Okay. So this is actually S star 1. Okay, for each of your interval, this is the formula, the S star. Okay, this is the S star 1, S star 2, and so on, right? So to get this S star T is actually the product, okay, where it is equals to, we start with 1, okay, because S star T is actually probability of T greater than or equals to T. So the total of probability is equals to 1. So therefore, we begin with 1. And then we times with the first survival function for the first interval, we will get the second S star T for the second interval, right? And then for the third interval is 0.6522 times 0.6154, okay? You will get the third S star T for the third interval and so on, right? This is your S star T, right? Okay, so once you're done with your S star T, what you need to do with that? Okay, so then you can proceed with the lifetime plot. All right, so I think there is a graph for the lifetime plot. Okay, so this graph look like a stairs, okay, or a step graph. Okay, so if you look at this graph, you can see that overall there is a decreasing function for the survival function. Okay, if you draw a smooth line, we can see it's a decreasing function. Okay, so you are having a 6 interval, right, which is 1 2 3 4 5 6 interval. Okay, so the time is from 0, from the starting of your study until end of study, right? So it's actually, we stop until 60 to 70. So 60 to 70, right? So here, these are actually the value of your S star T, okay? And this is the value of your time interval, your T, okay? The interval T. Okay, so this is actually your T. Okay, you are looking for this, you are plotting this S star T and this T. Okay, so here, this is the graph of your estimated of your life table estimates. Are you okay with that? Any questions so far before I move on to Kaplan-Meier plot? Okay, so if there is no question, let us move on. So I just flip through the lecture notes first, okay, for the second example. Okay, so example 2.1 regarding the pulmonary metastasis, you can look at the example which is available in textbook. Okay, you can refer it yourself, right? So for the third one, which is the Kaplan-Meier estimates of your survival function ST, okay, so this is slightly different with your life table. Okay, so here construct a series of time intervals such that each contain one death which occur at the start of an interval. So let M be the number of interval constructed. So here, if you look at this graph or the timeline, you can see this is actually the starting of the time origin, or maybe the you start your study, okay, and then this is the end of study, T6. Okay, so for here, say that as at T1, okay, there is one event happen, which is death, and at T2 it's a censoring observation where maybe a patient lost to follow up, and at time T3 there are two events occur. So here we name it as T1, where there is one event occur. Here it's a time at time T2 where there are two events occur here. Okay, so there are T2. At T4, one event occur. So here we call it T3. T5, there is a censoring observation, and T6, there is one event here, where here we have a total of 4 events for this example. Okay. Note here, number 1, TI is not given to censored data. Okay, so you can see here T in a bracket does not given to the censored observation. The first interval does not contain death. So you can see the interval here does not contain any death or events. Assume censored values occur just after death if they appear to occur at the same time when NI is calculated. So these are the 3 assumptions that you need to do for the Kaplan-Meier plot. Okay, these are slightly more requirement compared to the live table. Where live table, we just assume that your CJ is uniformly distributed for each of your interval. However, for Kaplan-Meier, you are calculating the events, right? So the number of observations are not counted, therefore you don't put T in a bracket, and then you must make sure the first interval does not have any events. And also you assume your events, okay, your censored value occur after death, okay? So the censored observation should occur after an event, okay? Right. So these are the notation used, right? So the NI represent the number who alive just before TI and so at risk at TI. Okay, so DI be the number of death in TI plus delta. So the probability of survival through this interval from TI plus delta is 1 minus DI over NI. Okay, and then from TI plus delta to TI plus 1, the estimated survival function is 1. Sorry, the estimated probability is 1. So the probability of survival from TI plus delta to TI plus 1 is PI 1 minus DI over NI. Okay. So assume that the deaths are independent. Okay. So your S hat T, so this is slightly different notation. Okay. If you put S star, that is for the live table. So S hat T is actually the Kaplan-Meier estimates. Okay. So S hat T equals to the product I from 1 until J, PI, J equals to 1 until your interval M. So T between from the first event until the last event. Okay. Now, this is the advantages in Kaplan-Meier, right? Right. Number 1, the advantages. Kaplan-Meier is better than live table when Kaplan-Meier method does not depend on grouping of data. So that is the Kaplan-Meier is better than live table, right? So it is equivalent to live table if they have at most 1 death per interval. And number 3, without censoring, Kaplan-Meier estimate is equivalent to the empirical survival function, which is equals to the S tilde T. Okay, the one that I have explained to you at the beginning. Okay, so these are the 3 Kaplan-Meiers. Okay, where you find it better when it does not depend on the group of data. It is equivalent when you have 1 event per time interval. And if there is no censoring, it is equivalent to the empirical survival function. Okay. Okay. So let us look at this example. Okay. So I just leave it free. Okay. Because you can refer this to example 2.3, and you can also look at the hepatitis data in first lecture. Right. Okay. So let us look at the hepatitis data set. Okay, so you look here, we have a data which has been sorted based on their survival time, right? So, and the star represent that the patient is still alive, while the hashtag represent that the patient was lost to follow up. Okay, so this star and hashtag represent censoring data. Okay. Now, right? So we have 2, 4, 10, 10, 22, 28, 29, 37, 40, 41, 54, 61, 63, and 32. So these are the given intervals 0, 2, 4, 10, 22, 29, and 37 because the maximum, so the maximum value of the survival time is 32, the minimum is 2. Okay, so we just list the intervals. Okay, we just start at 0 and end at 37. Okay, so if you see here, the interval doesn't have an equal length. Okay, so you can calculate the NI. Okay, so for the first NI, okay, since that we have, is that okay if I just go back and forth, right? So I'm so sorry about that because I cannot copy, because I want to use OneNote where can I just take a clip and then just copy and paste it. But I don't know why my OneNote drive does not working today. Okay, that's why I'm a bit messy today. I'm so sorry about that. Okay, I will improve my lecture style from time to time, right? So we have 14 patients. So we start with 14, okay? So here we have 2, 4, 10, 10, and then we have one event here, okay? Okay, I think I have this, yeah, I have this example, hepatitis data. This is the Nelson Allen, not this one. Okay, sorry about that. So before that, let us look at the example, because since that I already referred to the textbook, so why don't we refer to the first example regarding the usage of IUD? Okay, so the data of IUD represent in table 1.1. Okay, so table 1.1 is here. Okay, so 1.1 is here. So we have this table, right? Time in weeks to discontinuation of IUD. So as you know that IUD is actually one of the contraceptive method, right? So we have this, how many patients we have, sorry about that. Not here, not this data, okay. So we have this, if table table 2.2 is actually referring to example 1.1. Okay, so how are we calculating the time interval? We are actually list the time interval since that we have, how many patients? We have 18 women with the discontinuation of IUD. So we just list the time interval here. Okay, so here again, it is unequal time interval length. Okay, so the first thing that you need to calculate is you must have your first NJ. Okay, and then you can see the first interval. This is very messy, okay? Oh my God. Can I just click that? It's really annoying, okay? Where is my table 1.1? Okay, this one. Okay, so the first patient, the second patient is censored, okay? And then here, what you can do, you just list out all your NJ, right? So here, the first event, okay, we have the first event, which is at 10, okay, the first event, 10, and then the second one, 13, is censored, and then 18 is censored as well. So this is actually a sorted data, okay? So, right, so 10, 13, 18, right? So let me just have a quick check. Okay, so if you look here, okay, the first, this is the NJ. NJ is actually the number of death, right? Sorry, the number of patients, right? So yeah, okay, am I right, NJ? Yeah, the number who is alive. Okay, sorry. Okay, oh no, not this one. Okay, so since that we have 18 patients and the first event at the second intervals, right? So the first NJ is 18, okay? So the first event is 18 and there is no events here. So we just put here 0, and then to get the second NJ, it's actually 18 minus 0, which is equals to 18. Okay, and then if you refer to the table, okay, so the first DJ is equals to 10, right? And then we also have, if you realize here for the Kaplan-Meier estimates, you don't have to calculate your CJ, okay? So here your DJ is 0, and then the second interval, which is at 10, you have one event here, so which is equals to your NJ is still 18 because 18 minus 0 is 18, okay? So this is equals to 18 minus 0 minus is equals to 18, okay? So here, okay, at this interval, right, you have one event, okay? Since that from the second interval to the third interval, which is 19, okay, and then you have one event here, which is the event happened at time point 10, and then the next one is, I think we have two, if I'm not mistaken. Sorry about that. Oh, this is so frustrating, okay? I should just copy and paste, right? So if you see here, the first interval is, we have the first interval, the second interval, and then the third one is 19, okay? And then here, this is your interval, this is your NJ, okay? Since that we have 18 patients, so you just have 18 here, and then the DJ, okay, because the first interval doesn't have any events, so we just put here 0. So the second event happens at the second interval. So this actually fulfill the assumptions where um, there is no events in the first interval. Okay, so in this case, 18 minus 0 is still 18. Okay, and first event happened at interval number 2. So we put here 1. And then the second one is 19. So since that we have 1, 2, 3 events happen, which is 1 death and 2 censoring. Therefore, NJ is reduced not to 17, but it should minus censoring as well, which is equals to 15. Okay, so at 15, okay, at 19, you have 19, and the next one is, I just put it here, it's easier. Not this one, it's too fast. Okay. Oh my gosh. Okay, so we have 0, 10, 19, 30, 36, 59. Better write it down. Sorry about that. 30, 36, 59, 75, 93, 97, and 107. Okay, so I just put it here. What's going on? Okay, so we have 19, and the next one is 30. Okay, so I just want to show to you, here at the 19 interval, you have one event occur. Okay, so 19 to 30. So here is the next one. So here we have 15, and you must minus 1 and 2. So you here must have 13, right? 13. Okay, and at 30, you have one event again. Okay, so I continue here, just continue here. Okay, and then the next one is 36. Sorry, here, 36, which is equals to 36, which is 30 and 36, which is equals to 12. Yeah, because we have one event here, and then 36, and the next one is 59. Okay, so 59 dash, right? How many events? So the next one, 36, right? So 1, 2, 3, 4. So 12 minus 4 is 8. Okay, and how many events happen at 59? 1. Okay, and then the next one is 75. Okay, so you can carry on to calculate the NJ and DJ, which is 75, 93, 97, and so on. Okay, and then once you calculate, obtain NJ and DJ, you can get what is the S hat T. Okay, so this is the example of using the IUD. Okay, so referring back to this example, hepatitis data. Okay, so given a data, this is the given hepatitis data. So we have 2, 4, 10, and 28. Okay, so if you look at this table, 0, we have 14 survival. Okay, number of patient who is alive, which is 14. And then your DI is, there's no death occur. And then you can calculate your PI. PI is equals to 1 minus DI over NI. And your S hat T is your products of your PI. Okay, so this is the second one, which is 2. You have, again, this is 14. Okay, you have one event here. Okay, and then PI equals to 1 minus DI over NI. So 1 minus DI is 1 divided by 14. Okay, so it is equals to 0.9286. Okay, so when you calculate this, it is equals to the product of your PI. So this is equals to 0.9286 as well. Sorry, 9286. Okay, and then the next one at 4. Okay, if you refer to your table, okay, so 4 also one event happened. Okay, so 4, you have 14 minus 1 is 13. One event happened, so your PI is equals to 1 minus 1 over 13. That at that interval, so it is equals to 0.9286. 0.9231. Okay, and then to get the PI, it is equals to 0.9286 times with 0.9231. Which is equals to 0.8572. Okay, and the third one, which is at time point 10, you can see that there are two events occur. Okay, so here the value now is 12, which is 13 minus 1, which is equals to 12, and there are two events occur, right? So the PI is 1 minus 2 over nj, so 2 divided by 12, okay, which is equals to 0.833. Oh, okay. So to get the S hat T is 0.8576 times with 0.8333, which is equals to 0.7146. Okay, and then you can move on to the next one, which is the NG now, because there are two events happen. Therefore, the interval 22 equals to 10. Okay, right, right. So 22, there is one event. Okay, so one event occur, right? So the PI is 1 minus 1 over 10, which is equals to 0.9. Okay, and then you can see that 0.7146 times 0.9 is equals to 0.6431. Okay, so you might question me like, can we have like an slightly increasing PI? The answer, yes, you can. But since that the S hat T equals to the product of your PI, you can see that the value of your S hat T is actually decreasing over time. Okay. So for interval 29, okay, so interval 29, there are two events occur, which is we have 28 censoring here. So 29 is equals to 10 minus 2, which is 8. And then there is one event, right? Zero 0.875. Okay, and then the next one is 0.6431 times 0.875, which is equals to 0.5627. Okay, and the last one is at interval 37, okay, where we have ah oh okay, so the second one is 29, and then we have the last one at 37, right? So at 37 we have, sorry, we have um, two events there. Okay, so we have 8 minus 2 supposed to be 6, and we have one death there, right? So you can see it's quite tricky here. If you look here, right, suppose after 29 supposed to be 32, but 32 we purposely put it here. Okay, if you miss this 32, you will wrongly calculate, where you can assume that there are only one events, and you just simply minus one because there is one event here. But you can see there is one censoring occur at 32. So therefore, it's 8 minus 2, which is equals to 6. 6 here, and there is one event happens, okay, at 37. So the value is 1 minus 1 over 6, which is equals to 0.833 again. Okay, times 0.5627 equals to 0.4689. Okay, and then after that, you can just plot the S hat t against your t. This is S hat t, okay? And depends on the interval that you have. Where's my graph? You have 0, 2, 4, 10, 22. Just put here 0, 2, 4, 10, 22. No, 0, 2, 4, 10, 22, 29, and 37. Okay, so here we can start. Sorry about that. Okay, 0 should be at time origin. Okay. Oh, I have to do it again. So it's already 8 o'clock. Okay, we need to stop our lesson now. Okay, and maybe you can look at the example, and also I have shared with you some log rank self-learning on how to do the log rank. Okay, so 0, 2, 4. Okay, because I need to stop now. I need to perform my solat. Right, 0, 2, 4, 10, 22. 10, 22, 29, and this is 37. Okay, so you just simply plot that based on the calculation. Okay, the first one is 0.9286. So here is 1. Okay, so you can have, sorry. Okay, 0 to 2 is 1. Okay, and then the next one is 0.92. Apa tadi? 0.9286. Okay, so it's slightly down, which is here, 0.9286, right? And then you move on to the next one, which is 4, and then and so on. Okay, so I think like you can see that your S hat T is actually in a decreasing pattern. Okay, don't draw like this one. Okay, I just want to tell you that you must have like a step graph, but you must tell that the trend is actually decreasing as the time survival time increasing. Okay, so I think like I will share with you these lecture notes so that you can try on this exercise. Okay, for the remaining 1 hour left for our lecture. So I think like for the live tutorial lecture, I think we should stop here so that you can look at the example based on the lecture notes. Okay, here there are 2 examples for live table and 2 examples for Kaplan-Meier survival curve. Okay, so I will continue next week with the standard error of Kaplan-Meier, which is the Greenwood formula, and also the confidence interval for the estimation survival function. And also we are going to look at the hazard function for both live table and Kaplan-Meier Kaplan-Meier hazard function. Okay, so that's all for today's class, right? So I'm so sorry. There is a lot of technical problem here where I cannot use my OneDrive, or else I can just simply click the data set and also calculate the table easily to demonstrate to you. And also I will post this lecture note where I thought that this lecture note is already available in your Spectrum. However, this lecture note is not uploaded in the Spectrum. Sorry about that. So you can refer to these lecture notes to do your estimated survival function. Okay, so thank you so much, class. And yeah, you can use the last 1 hour to practice these two estimated survival function using Kaplan-Meier and live table. Right, so if you have any question, you can just simply DM me regarding these two problems. Right, so thank you so much for that, and bye for now.